Welcome back to Asteroid Day Live 2021. I'm Lisa Burke. Having heard about how we find and track asteroids, we're now going to hear about how scientists go about investigating them. Once the space race began, it was really only a matter of time before planetary scientists sent a space probe to the asteroids. That moment came on the 17th of February 1996 with the launch of NASA's NEAR-Shoemaker spacecraft to asteroid Eros. As a result, our investigation of asteroids changed forever. In this second part of Asteroid Day Live 2021, we'll get to know the asteroids better than ever before and begin to see them as a diverse population of intriguing mini-worlds, each with a story to tell. We'll hear from scientists in Japan and America about the remarkable successes of the Hayabusa 2 and OSIRIS-REx missions. And we'll talk to Asteroid Day's co-founder and Queen guitarist, Brian May, about his work turning asteroid data into three-dimensional images. First, we hear from Julia de Leon, a planetary scientist at the Instituto de Astrofísica de Canarias, about how we get to know the asteroids.
Today, astronomers can use many techniques to get to know the asteroids better. Perhaps the most powerful is spectroscopy. This is where we split the light from the asteroid into a rainbow of colors. And part of this light is absorbed by the materials on the surface of the asteroid and leave kind of dark and white stripes. They look a bit like shopping barcodes. Instead of the price of the shopping, these fans reveal the composition of the asteroid surface. We can also measure how the brightness of the asteroid changes with time, something that we call a light curve. Asteroids reflect the light of the sun on their surfaces, and mainly because they are irregular bodies and they are rotating and they present different orientations towards us, the amount of reflected light or the brightness of the asteroid changes with time. So by obtaining light curves, we know how much time it takes the asteroid to spin or rotate, and we can even infer its shape. We call these and other techniques of these processes characterization. And it has revealed that asteroids come in many different shapes and sizes and even compositions.
I'm back with Andy Chang, the lead investigator for NASA's DART mission and the former project scientist for the world's first ever dedicated asteroid mission, NEAR-Shoemaker, which celebrates its 25th launch anniversary this year. Andy, let's wind the clock back for a moment to before the launch of NEAR and give us a picture of what we knew about the makeup of asteroids back then.
We had big questions about the nature of the asteroids. One of these questions was the connection between asteroids and meteorites. The most common meteorites, these are rocks that fall onto Earth from space. We now understand they are pieces of asteroids. But that itself was puzzling. What was puzzling about it was that the most common asteroids and that we see in telescopes and the most common meteorites whose composition we measure after they fall on the Earth, they did not seem to match. And so how is that possible? And we now understand after NEAR that the compositions actually do match, but they don't look that way. The surfaces of these rocks, these minerals are altered by exposure to space radiation. So they look different in telescopes than what we had realized. But the elemental composition matches, and we have also since NEAR returned samples from a number of the same kind of stony asteroids, the S-type asteroids, and in fact confirmed that the compositions do match with the most common meteorites. So that's a mystery solved.
What's the difference in the range of differences in the compositions of the asteroids? Because they come in many different types, don't they?
Asteroids come in many different types. And actually, if you just think back to all the different types of materials and rocks you find on a planet like the Earth, how many different kinds? In the asteroid belt also, you find a similarly large diversity of materials, some of which came from the surfaces or similar to the materials you find on the surfaces of a planet. Others are similar to what you find in the deeper layers or even in the core of a planet. And so that's that full diversity. And of the surface materials, some asteroids have a lot of water in them. They have clays. They have minerals that have been altered by contact with liquid water. And those are very common. So there's a tremendous diversity. Some asteroids are carbonaceous. So they're dark and they have a lot of organic materials on the surface. And others are rocky, like the asteroid that NEAR visited was a asteroid with one of these rocky surfaces. We now understand that surface also was one which was not ever melted. That was one of the big questions also for NEAR, was whether an asteroid like Eros would be made out of what we call differentiated material. Differentiated means that it melted and it's separated, like oil and water separate, so that the denser materials, iron-rich materials, settle into the core of a planet. This happened on Earth, this happened on Mars. Whereas the lighter rocky materials are on the top of such a body, a differentiated body. The question is, was Eros part of a differentiated body at one time? And also from NEAR now we know it was not. It was the more primitive type before these materials separate.
Absolutely fascinating.
Yes.
So it's a truly old object dating back
Yes.
billions
Really
of
old
years.
object, yes.
And it's not just the launch anniversary this year of NEAR, is it? It's also the 20th landing anniversary as well, because you actually put your spacecraft down onto the surface of Eros, something that the spacecraft was not designed to do. I'd love to hear a little bit of that story and what, if any, science that you could get out of that maneuver.
Yes, NEAR was the first landing on an asteroid. It was something that was we decided here at APL, Bob Farquhar, who was the mission manager, and we decided very early on that we had to land the spacecraft on the asteroid. However, the idea was so terrifying, and we were not officially allowed to announce that we were going to attempt a landing. In fact, we were not allowed to call it a landing. It was a controlled descent. That was all we were allowed to say. Controlled descent to the surface. And then when we actually landed, it did it. And it turned out to be very important for the science that we were able to land the spacecraft, because there was a very important measurement with the gamma ray spectrometer that actually could not be made successfully while the spacecraft was in orbit. It turned out that the level of signals that we were receiving from the elements we wanted to measure were not as high as expected. And so in orbit, we were not able to really pin down the composition of the asteroid. But once it went down on the surface, signals were stronger, and we were able to make measurements for a period of 2 weeks on the surface of the asteroid. And that's what really pinned down the composition. It was a very important sign for science that we were able to land. And of course, for other missions now, they know it's possible to do this. They know how NEAR did it. And in fact, very similar methods are used by all the other missions that have since landed on asteroids. They've taken samples, they've done surface science, fantastic things. But NEAR was the first to show how to do these proximity operations near an asteroid. And someday we may actually decide to try to extract resources from an asteroid. Try to do mining on an asteroid. You do the same, very similar things again. You have to get close to the surface, descend, put your spacecraft down, and do what you need to do.
Fantastic. Great, great achievement and a great mission. So, Andy, thank you very much.
Asteroids come in a wide range of types. The composition is extremely varied, but falls into two main groups or types. Carbonaceous or C-type asteroids are maybe the most interesting. This consists of clays and other hydrated minerals, carbon compounds, and even organic material. Their surfaces are quite dark, reflecting less than 10% of the light of the sun, and they are thought to be largely unchanged since the origin of the solar system, and that's why they are so interesting. NASA's OSIRIS-REx mission visited the carbonaceous asteroid Bennu in 2018, and will be bringing back samples of this asteroid in 2023. The other group, the stony or S-type asteroids, are made up of silicate materials and nickel, iron, and metal. They are probably fragments of once larger asteroids. And these bodies were actually the first to be visited by a spacecraft, like NASA's NEAR-Shoemaker mission to asteroid Eros, or in 2000, or the JAXA's Hayabusa mission to Itokawa in 2005. There are a number of other interesting types of asteroids. For example, the metallic M-type asteroids are entirely made of nickel iron, and they could be from the core of a large planetesimal that was shattered in a collision. Actually, NASA will send a mission next year to study these metallic bodies, in particular asteroid Psyche. We used to think that asteroids cannot have ices because mainly due to their location, because they are mainly concentrated between the orbits of Mars and Jupiter, and at those distances, temperatures are so high that ices cannot survive. This was the dividing line between comets that do carry ices and asteroids. But in the last years, we have discovered asteroids that suddenly present or show cometary activity, or we have even discovered and detected ices on the surface of large asteroids like Ceres or asteroid Themis, meaning that the dividing line between comets and asteroids is not as sharp as we once thought.
Well, it'd be very hard to walk on an asteroid. I mean, it's just a smidgen of gravity, and it would be really difficult to, almost impossible. If you think of like the Earth's gravity, the moon's gravity is like 16% of the Earth's, and Mars is 38% of the Earth's. It's like 9.8 meters per second squared. It's pulling you down onto the Earth. So think of 3% of the Earth's gravity. If you were trying to walk on that, you would take a step and launch yourself up. So like we do in space on the space station with spacewalks, astronauts have to tether themselves to keep from floating off. And so that's exactly what we'd have to do on an asteroid. We have to tether ourselves to the asteroid to move around, because it's only a very minuscule amount of gravity that's holding you down. So if you really wanted to dunk a basketball on a maybe 1,000-foot goal, maybe 500-foot goal, you could launch off and do it, but you would definitely want to be tethered to come back down.
Bennu is a near-Earth asteroid, about half a kilometer or a third of a mile in length. It has an extremely dark surface, made of carbon-rich material that probably dates back to the very beginning of our solar system. Bennu could contain the types of molecules that led to the formation of life on Earth. Because of Bennu's rare composition and its proximity in orbit to Earth, NASA chose it as the destination for its OSIRIS-REx sample return mission. In October 2020, OSIRIS-REx touched the surface of Bennu and collected more than 60 grams of material. This sample is now on its way back to Earth and will parachute into the Utah desert on September 24th, 2023. Bennu will pass by Earth in 2060 at about twice the distance of the Moon, but in the latter part of the 22nd century, there is a tiny chance that Bennu could impact our planet. That's all the more reason to keep a close eye on Bennu. But for now, scientists are eagerly awaiting the samples to tell them more about the formation of the Earth and maybe even the formation of life itself.
There's an old saying that seeing is believing, and this is every bit as true in astronomy and the study of asteroids as it is in every other walk of life. But where astronomers are concerned, imaging is a crucial endeavor because it gives context and allows the data from other instruments to be better understood. To talk about this further, I'm joined now by two people who have taken the imaging of asteroids and data visualization to a whole new level. Patrick Michel is Research Director at CNRS at the Côte d'Azur Observatory, and Brian May is an astrophysicist, guitarist with Queen, and co-founder of Asteroid Day. He's also an expert in stereoscopic imaging. So Brian, briefly, what is a stereoscopic image?
I'm glad you asked, Stuart. There's another old saying, which is there's nothing new under the sun, right? And stereoscopic images go back to 1832, when Charles Wheatstone discovered the principle of stereopsis, which had eluded the whole of the Renaissance, which still amazes me. And basically, it's the fact that we have two eyes for a very good reason. And the reason is that they give us depth perception, instinctive depth perception. And the two eyes give us two slightly different views of the universe around us. And our brain constantly, every second of our lives, combines these two slightly different images and makes them into one in-depth image inside our brains. It's a miracle. It really is. And something which is very, very often overlooked. Most of the imaging that is done, even in the 21st century, is mono. It's as if you had one eye. But as soon as you go back to using your two eyes, as the Victorians did, you get a whole world revealed to you, because it's the real world. And it's always a sort of surprise to me that there's so much emphasis on mono imaging when we are stereoscopic people, we are stereoscopic animals. So the business of imaging in astronomy comes down to getting the right baseline. And should I go into this? I mean,
well, I did have a question for you about baselines. So yeah, let's tell us all about this, because this is fascinating.
Could just launch in. Yeah, the idea of a baseline is it's the distance between the two viewpoints. So in the case of our two eyes, our baseline is about 2.5 inches, vary slightly from person to person. So if you have a camera with two lenses 2.5 inches apart, it will take two pictures which will correspond to the real images we would get into our brains if we were there. The genius of Charles Wheatstone was to present these two images from two lenses individually to each eye, so that our brains can do the same amazing miracle on the stereo images as they did on the scene when we were there. Now, the baseline of our eyes is not good enough for anything further away than the trees over there on the horizon, because you're not giving your brain much information which is different from eye to eye. So what we do is we lengthen the baseline. To see those trees over there, we'll lengthen it to a few feet maybe, and suddenly we'll see a nice stereoscopic image of the trees bouncing out towards us. But if we want to look at the moon, which is 250,000 miles away, we've got to have our baseline of the order of 250,000 miles, a few tens of thousands of miles. How do you do that? Well, various ways. That's where the ingenuity comes in. And with almost with every astronomical object in the solar system around us, it will give us an opportunity to get that baseline. The moon gives it to us because it wobbles, it liberates, and so it offers two slightly different views without us even moving. And you put those two together a couple of months apart at the same phase, and you get a beautiful stereoscopic image of the moon. Other things we have to approach in different ways, but we have so many probes out there now, out in the solar system, thanks to NASA and ESA and JAXA. They all move around various objects, and they give us opportunities for finding the right baseline to see these objects in glorious 3D. And it's sensational when you see it.
It certainly is. I mean, it really does bring these objects to life and makes you appreciate, at one level, how big these rocks are in space, but also at another level, how small they are in comparison to other celestial objects, because you can really see the curvature on them towards the horizons. And Patrick, if I could turn to you now, because there's real scientific value in these stereoscopic images, isn't there?
Yeah, absolutely. I mean, Brian made me realize the value of seeing in 3D. And in fact, what's fascinating is the fact that we go to explore totally new territories, which are very far away from Earth and which evolve in very different conditions than Earth. So in 2D, it's very hard to really access all the information we need to access in order to understand them. But of course, we are used to see images in 2Ds, so it seems, okay, we can do something with it. And then when Brian gave me the first 3D images of the asteroid Ryugu that was explored by Hayabusa 2, I mean, I was absolutely amazing. As I said, I fell from my chair. I was totally excited because then it reveals again another world. So you first have the first surprise of seeing for the first time 2D images of a new world. And then you put these glasses, and with the art of Brian doing the stereo imaging, you just look into that and you are in a totally different universe. And that's very important because it's very hard to understand what we see. The geology of these bodies is really totally crazy. We still have problem to understand that. So having all the dimensions is really crucial. And it actually helped us also to better understand where we could land to get some samples. Because when we have some constraints about the height of the boulders on the asteroids, we had to find rooms, places where the boulders are not higher than 70 centimeters in size. Of course, on 2D images, it's quite complicated. You can try with the shadows, etc. With 3D images, of course, you have a better perception of the height. And Brian helped a lot for both Hayabusa 2 and OSIRIS-REx to find the sampling sites. So there is a really, really good uses of these images. And plus, you know, what's really striking is when you see these images in 2D, and then you put these glasses and you see them in 3D, it's really a feeling that cannot be described in words. It's really exciting.
It's just like it's suddenly there in front of you, you know, and you have a real physical sense that I do, is that you could reach out and sort of really just touch this thing. It just looks so real. Now, Brian, you mentioned baseline earlier, and I just want to return to that briefly now, because one of the things that I think is most ingenious about this, and again, you have touched on this, but I want you to emphasize this a little bit, because I want everyone who's watching to understand that how clever this is that you're making 3D images from a spacecraft that sort of has just one camera, and you're using motion to create your baseline. Talk us through that process, how you identify that, how you sort through images to know which might make good stereoscopic pairs. Sort of open the curtains a little bit and take us in behind the scenes of how you do this.
Yeah, well, I'm lucky in having a very great colleague, a great accomplice called Claudia Manzoni. And what she does is trawl through the archives of various missions, sometimes while they're being created, but sometimes a long time afterwards, like in the case of the Apollo missions, for instance. And she looks for two images which will work as a stereo pair. So she's looking for two images which have been taken with the right baseline that will give us an opportunity to make these images. From then on, it's not so hard. Well, it's still hard, but she's done the difficult bit, really, you know, which is actually finding these images which will work. The problem that we usually get is by the time this is sequential imaging, you know, you're taking one picture, the left-hand side, and then something moves and you take the right-hand side. So things will have changed in between. That's the only problem. Now, not much changes on the moon, not much changes on an inert asteroid, but what does change a lot is the illumination. The lighting will change because these things are all rotating. And mostly, like in the case of Rosetta, with Bennu, with OSIRIS-REx, with Ryugu, they're rotating faster than anything can move around them. So you always get a stereo pair, which is difficult to view because the shadows are all different from eye to eye. You get this thing called retinal rivalry. Your two eyes are seeing two things which they can't really reconcile. So what I have to do then is to go through, and generally it's a manual process. I have to map the shadows from one side to the other to make them match up, to make them fall on the right piece of ground. And it's an annoyingly repetitive process, but I'm quite good at annoyingly repetitive processes. It seems to be my sort of dogged instinct. It takes over. And I've done it with Victorian images, which are covered in dust and various kinds of pollution. I've been known to spend weeks on one particular image restoring it by getting rid of all the glitches. So it's the same thing in this case, really. By the time I spend a few hours, hopefully a few hours, all the shadows are matched up, and then you get your perfect image. It needs to be aligned because things are never going to be quite right. And you need to do a little bit of sorting out to make sure that the parallax differences, as they're called, are all in one plane. Because our eyes are very good at sorting out distances due to movement this way. They're not very good at sorting out distances vertically, unless we view it like this, which we don't want to do. So you have to arrange that everything is aligned perfectly, take care of the shadows, and then we get our lovely pristine stereoscopic image if we're lucky.
It's absolutely fascinating, the amount of work that really goes into it. And Patrick, you have started extending this as well, beyond just actual images, but into data visualization and model results as well, I believe.
Yeah, absolutely. And what's fascinating is to see. I'm lucky to be the witness of Claudia and Brian working together. When I give them some new movies or simulation, they are, of course, are perfectionists, so I'm never super happy. And so they start something, and then I look in the glasses, looks perfect, and then Claudia says, no, that's not real correct, and then Brian, etc., until they are happy. And that allows me to measure the complexity of the process, especially with movies, where so basically we investigated the three kinds of processes. So one is how an asteroid disrupts, and then its fragments reaccumulate to form these rubble piles that are the current asteroids that we visit now. And doing it with a stereo is fantastic because then you really see in 3D the shapes of the fragments you are creating the disruption, and you can compare them with the shapes of Ryugu and Bennu. And of course, 3D is important because they have really specific geological properties like a ridge at the equator. So we want to reproduce that. And so that's the first process. The second one is also when these bodies have their rotation rate that increases due to a thermal effect called the York effect. Then we want to see how, because the centrifugal force exceeds the gravity, how they reshape, basically, how they shed mass, etc. And again, for this, you want to be in 3D because you want to see the velocities of these particles in all the directions. And that's very important. Actually, we made a paper with Brian, Claudia, and others, and Yoon Zong, my postdoc, where we showed this simulation because one of the rhetoric was saying, look, in your 2D movies, we don't have the perception of the velocities of these ejecta that go away from the asteroid. And with the stereo image, immediately said, oh, that's fantastic. Now I understand everything. So that's really nice. And the other one is also tidal encounters with planets. As you know, Apophis is going to come very close to the Earth in 2029. And we are interested to know what happens when a body comes very close to a planet, how possibly the tidal force can make some surface motion or even reshape the body. And again, we made some simulation, and seeing that with stereo pairs in 3D is absolutely fantastic to see exactly how in all the dimensions the body reshapes, which is very important scientifically. And what I measured is the fact that, of course, during a movie, the particles fly in all directions. So how can you do stereo pairs with that? So typically we send the movies filmed in two different directions, and we try to find an angle that is large enough, but not small enough to be able to do stereoscopy. But then I could measure with the interaction between Brian and Claudia how challenging it is. And I'm very sorry for that, but I think they had fun.
Yeah, one of the things I was going to say, Brian, is that going from images that don't move to a whole movie where things are flying around, all over the place. Gosh, how did you sort that all out?
Well, really, Patrick sorted it for us. I always say, fun is a very important word here. This is great fun to us. It's not really rocket science. It's Victorian technology applied to modern science. And what happens is you get something very human happening. That's why I love it most of all, I think, because it brings instinct back into it. You can look at this thing. You could look at a pile of graphs telling you where all these particles went. You could look at lots of equations telling you what was happening. But as soon as you see it in 3D and you think, oh God, these come out here and those go out there, you get this instinctive feeling, which is an enormous advance, really, because science advances sometimes best through answering questions, in fact, through asking the right questions. But the questions are very often answered by an instinct, and then the details are filled in afterwards. You need that flash of inspiration, and that's the kind of thing that I think stereoscopy can give you. So to me, it is fun, definitely. And the fact that it's a movie rather than a stationary object is taken care of by the fact that we've set it up right. Patrick has set up his simulations right. We have aligned them. So then you just stand back and watch it happen, and everything will happen right because it's in the right frame.
And you're both involved in the ESA mission Hera as well. So can we expect some lovely stereoscopic images of the asteroid Didymos?
Certainly hope so, yes. This is all in the future. And some of these stereoscopic opportunities are built into missions these days, but some of them are not. And in fact, very often the greatest moments happen because there's an opportunity that nobody foresaw before. So I think we can rely on a lot of sort of opportunism in these missions. Yes, I think everyone's aware that we're going to be looking for stereoscopic images, but there will be a moment when the craft pulls up beside and then perhaps goes into an orbit around Didymos, and we get the first two images which are separated by the right kind of baseline. And for the first time, we'll have that glorious moment of seeing what Didymos actually looks like. Amazing. Can't wait.
Yeah, absolutely. And what's going to be fun is to compare our modeling of Didymos, and we are actually now implementing a new model where we have both the primary and the small moon of Didymos. The first simulation we did with Brian were just the primary. Now we include both of them, and doing stereo pairs of that and comparing with the real world is going to be exciting. Probably it will be all wrong, but that's okay. And then we also have another opportunity for stereo pair that's going to be fantastic, is that we are now developing a rover with CNES, the French Space Agency, and DLR in Germany, to be put on Phobos by the Japanese mission MMX, which is a Phobos sample return mission. So in 2026, 2027, we'll be on the surface of Phobos, and we have two navigation cameras that can do stereo. So Brian, we count on you to make us dream again with the scenery of Phobos in 3D. That's going to be also amazing.
Wow, yes, please.
So, a lot of fun.
I will come to Phobos with great pleasure.
It sounds to me, Brian, like you are going to be a very busy man for the next few years, and you are as well, Patrick.
Absolutely, but it's a good business.
It's a very nice business to be in, yeah.
Absolutely. Gentlemen, I can't thank you enough for your time today. Patrick, you are a relentless asteroid researcher. The work you have done is unparalleled. Brian, you co-founded this day, and you continue to work so hard on astronomy outreach and on all the asteroids and the stereoscopic imaging. So again, I know you're both super busy people, and it gives us great pleasure to see you today and to say thank you so much for being with us.
Thank you, Stuart. Very well done.
Thank you. Thank you, Brian, too.
I'm joined now by Xavier Thielen, Head of Production and Digital Media Operations at Broadcasting Centre in Europe. Xavier, so lovely to have you here with me in the studio.
Hello, Lisa. The same for me. It is very nice that you are back in the studio to produce in live for Asteroid Day Live out of BCE Studios here in RTL City.
It's just wonderful to be here, and this is actually the 4th year that you've provided us this facility, the BCE Studios. And of course, last year it was lockdown. This year we're sort of semi-lockdown. How has the pandemic changed what you do at BCE?
First of all, I would like to say I'm happy that the quality has not changed, and we were able over the whole pandemic to have all our channels on air without any incident. I think that's due to high skilled engineering that we are producing in BCE, and definitely as well about the dedicated staff, which was available 100% over all the time.
And we've been looking throughout this program at the future of research for asteroids in space economy. When we think about the future of broadcasting for BCE, what do you think about?
So, talking again about the change, the last 15 months was challenging. We needed to be able to provide as much operational out of home office. That means we went to cloud processing more and more. And that is as well, I think, a dedication for the next months or years to come to bring broadcast and production tools to cloud processing wherever possible. The second part, I think, for production, talking about space, that means waves. 5G technology is coming up, and that will allow us to become more efficient in remote production, allowing that you just bring the cameras and the sound on field and bring all signals via 5G to a remote production site, or, for example, here, bringing in the signals to RTL City. So I think that's two topics that will definitely keep us busy over the next year.
Absolutely. And when it comes to Asteroid Day, why is it important for you to be a sponsor, to be a host for us?
I think, as I have mentioned in the past already, as we are an engineering company, we are interested in helping to develop for humanity and for the future, and I think that's why we stay with you. We wish you a very happy day this year, and hopefully you can come back to us in a full hybrid vision version again next year.
That would be wonderful, and it's what we're all looking forward to. Xavier, thank you so much once more for your time and these fantastic facilities. We're so very, very grateful from the whole team here at Asteroid Day for your support. Now we're going to hear from Makoto Yoshikawa with an update on JAXA's Hayabusa 2 mission.
2020年12月6日に JAXA の話題のはやぶさ2ミッションは小惑星リュウグウのサンプルを採集するのに成功し、地球に帰還しました。もともと 0.1 グラムを採集するのを目標に設定しましたが、それをはるかに上回る 5.4 グラムも採集できました。月以外の天体から、これほどの量を地球に持って帰ってくるのは人類初の功績です。小惑星の研究者にとって、このサンプルはものすごく重要で、分析により46億年前の惑星の形成から遡る秘密を解き明かすことになり得ます。この神々しい功績についてお話しするのは、はやぶさ2ミッションマネージャーの、吉川誠先生です。本日はご参加いただき誠にありがとうございます。はやぶさ2に、よって採集したサンプルは現在どこにあるのでしょうか。
はい。現在5月末ですけれども、サンプルはまだ JAXA 相模原キャンパスですね、宇宙科学研究所のキュレーションという施設の中にあります。
なるほど。そのサンプルの化学組成は重要だと思いますが、かなり異なる地球の環境からどうやって汚染されないように保護するのでしょうか。
はい。これが非常に重要でして、はやぶさ2の場合はですね、サンプルが入るサンプルコンテナというところがあるんですが、これを非常に密閉性の良いものにしました。なので、カプセルが地球の大気に入ってきてもですね、そのサンプルコンテナの中に、空気がですね、入らないようになってるわけですね。でそれを今度はキュレーションシステムの中の、キュレーション施設の中の、クリーンチャンバーというところに入れます。でそのチャンバーの中は、最初は真空なんですね。真空の中で少しのサンプルを取り出して、その後は、チャンバーの中をですね、シストにします。シストの中で取り出すので、例えば酸素とかとは触れないんですね。 そのことによって、小惑星から取ってきたサンプルを地球の物質とはですね、当たらないようにしたということになります。
だいぶ保護されてますね。すごいですね。これから分析すると思いますが、いろんなことがわかると思いますが、一番期待しているのは何でしょうか？
そうですね。やはり、リュウグウに有機物とか水があるかどうかですね。今回のサンプルリターンは、リュウグウという小惑星に行ったわけですけれども、これはC 型小惑星といってですね、炭素を含んでいる小惑星なんですね。なので、我々が一番期待しているのは有機物です。それも、太陽系が生まれた頃ですね、今から46億年前にあった有機物でして、つまり地球生命のよりも前にですね、存在していたものということで、これは地球生命の起源を、調べる上でも、もしかすると何か、手がかりを与えてくれるかもしれない。そう期待しています。
素晴らしいですね。ものすごく期待できますね。それを分析するのにどれくらい時間かかるのでしょうか？
はい。分析は、まずははやぶさ2の初期分析チームというところで行うんですけれども、その初期分析がですね、6月から始まるんですね。で、一応1年間、時間を取っていまして、1年をかけて詳しい分析をする予定です。
はい、ありがとうございます。吉川先生は確かに、このミッション、長年関わってきたと思いますが、カプセルがようやく地球に帰ってきて、それを見てどんな気分でしたか？それに、カプセルが地球大気に突入する時の、カプセルからの光も見ましたか？
はい。残念ながらですね、私はオーストラリアに行ってないんですね。カプセル、オーストラリアのウーメラというところに戻ってきたんですけれども、そこに行けばですね、カプセルが大気に突入して、流れ星になるのが見えたんですが、本当は行きたかったんですね。ですが、今、新型コロナウイルスということで、オーストラリアにメンバーの数をですね、減らしたんですね。なので、残念ながら私はオーストラリアに行けずにですね、この JAXA、相模原キャンパスの方で、カプセルの期間を待ってました。でも、カプセルがですね、日本に戻ってきて、実物を見たら、やっぱりほっとしました。さらに、その中にサンプルも入っていましたので、これでミッションが大成功だということが確信できたわけですね。
もう、すごい良かったですね。やっぱり。いやー、ありがとうございます。吉川先生は確かに、ずっとアストロイドデーを支持してきたと思いますが、吉川先生にとってなぜアストロイドデーが大切なのでしょうか？
はい。実はですね、私はもう大学院に入ってですね、修士課程からずっと小惑星の研究をやっていたんですね。それも小惑星の軌道計算ということをやっていて、もう1990年代ぐらいからですね、このスペースガード、あるいはプラネタリーディフェンスということに興味を持っていました。これは、やはり天体が地球にぶつかると非常に大きな災害になる。その災害を事前に予測できるわけですよね。なので、これこそですね、事前に災害を予測して、我々の被害をですね、最小限にしたいと。そういうことがあって、私自身、アステロイドで非常に重要な活動だと思っています。
なるほど。わかりました。ありがとうございます。アストロイドデーの皆様も、吉川先生と、はやぶさ2チーム全員の功績を称えるとともに、分析の幸運を祈っております。私もおそらく世界中の人々も、その分析の結果を楽しみに待っております。本日はお時間を作っていただき、誠にありがとうございました。
どうもありがとうございました。
On October 20th, 2020, NASA's OSIRIS-REx spacecraft collected a sample from asteroid Bennu.
Navigation.
Stand go for tag.
Program manager.
Program manager is go for tag.
All stations, this is OREX Systems on OREX Chord. I copy all subsystems are go for tag.
Position uncertainty.
is 0.5 meters. Predicted tag lateral offset is 1.7 meters. Hazard probability is 0%.
OSIRIS-REx's sampling mechanism penetrated Bennu's regolith and fired its nitrogen gas bottle to stir up sample material for collection in the TAG-SAM head. At 6:08 p.m. Eastern, the team on Earth received confirmation of a successful touchdown.
OREX has descended below the 5-meter mark. The hazard map is go for tag.
And we have
After spending approximately 6 seconds at the surface, OSIRIS-REx fired its thrusters and backed away from sample site Nightingale. Images taken a few days later by the SAMCAM camera showed rocks and dust escaping the sampler head. The team believed it collected a sufficient sample and decided to seal the TAG-SAM to preserve the remaining material. The spacecraft made one more flyover of Bennu and saw just how big a mark it left on the asteroid's surface. The TAG event sent boulders flying across Nightingale's surface. OSIRIS-REx completed its last flyover of Bennu at around 6 a.m. Eastern on April 7, 2021, and slowly began drifting away from the asteroid. On May 10, 2021, OSIRIS-REx fired its thrusters and began its 2-year cruise back home to Earth. As OSIRIS-REx approaches Earth, it will jettison the sample return capsule that contains pieces from asteroid Bennu. The SRC will then travel through Earth's atmosphere and land under parachutes at the Utah Test and Training Range on September 24, 2023. Once recovered, the capsule will be transported to the curation facility at NASA's Johnson Space Center, where the sample will be removed for distribution to laboratories worldwide, enabling scientists to study the formation of our solar system and Earth as a habitable planet.
I'm joined now by Dante Loretta from the University of Arizona and the principal investigator of the OSIRIS-REx mission. Dante, thanks for being with us again on Asteroid Day Live. We really appreciate your time.
It's my pleasure, Stuart.
Now, last year, when you were here with us on Asteroid Day, you were telling us all about the painstaking preparations that you were making for the TAG maneuver and that sample collection. And then in October 2020, you pulled it off. So congratulations on that. Tell me about that day. I'm guessing that was quite something.
Yeah, thanks, Stuart. October 20th of 2020 was the culmination personally of over 17 years of work, not just by myself, but as you know, projects like this involve teams of thousands of people all around the globe. And it was exciting, it was nerve-wracking, and it went exactly as we had hoped. It was a really successful sampling event, and we're confident we got a lot of Bennu regolith in our collector.
Were there any surprises at all? Is there anything that you needed to have a double think about, or or did it all just go straight according to plan?
Well, Bennu has been a trickster since we arrived. It's always literally throwing curveballs at us in some cases, and the TAG event was no exception. For me, immediately upon contact, when I saw those images coming down, I was struck by how soft and compliant the surface was. There was really no resistance to our TAG-SAM collection device pushing down into the regolith. I like to use the analogy of one of those ball pits at a children's playground, which is basically how the surface responded. So that was really interesting and informed our knowledge a lot about the nature of these asteroid surfaces.
It's really fascinating, isn't it? Because we've been hearing from other people that that's a product of the weak gravity, perhaps, on the surface there, that the regolith, these broken parts of the surface, act maybe even like a fluid almost.
Yeah, exactly. Very fluid-like response of the surface. And we knew about the microgravity, but we thought that there would be some kind of cohesion between the particles, something that's kind of binding them together. But they seem like they just flow right past each other like marbles. There's no stickiness to the grains amongst themselves.
It's so amazing, these asteroids. The more we get to know about them, the more exotic they are. They're just such fascinating worlds in their own right. And when you got your crop of the regolith, your harvest, you then decided to stow straight away. You didn't need to go down and get any more. That's tell me about that decision.
Right. So 2 days after the sample collection event, we used our SAMCAM instrument to image the bottom of the sample collector. And at first we were getting excited because we could see some large particles that were clearly collected. And then as we brought down the longer exposure images, we started to see that there was a lot of material that was literally spewing out of the collector and into space. And I started to, really panic when I saw that, because I was like, man, this great sample that we collected is now being lost. So we had to expedite the stow procedure to preserve as much material as possible.
Well, as you say, Bennu's always giving you curveballs, but it's now safely stored. So bring me completely up to date with where you are on the mission. You've left orbit now, I think, and you're on your way back to Earth.
Yeah, we went back one last time. I talked to the team and I said, we need to go back and just document what the state of the surface looks like post-tag after everything had settled down. So on April 7th of 2021, we sent the spacecraft back for one final look at the asteroid. And we brought a great data set down, which showed us very clearly the extent of the surface disturbance. And that was what I called the farewell tour. That was the final look at Bennu, the last chance to collect any scientific data. And then on May 10th of 2021, we fired our main engine thrusters and began our journey back to Earth. And so we're now in interplanetary space, basically on cruise control for the next couple of years.
Fantastic. So the spacecraft cruising home. I bet you and your team are not on cruise control, though. Tell me about the preparations that you're making here on Earth.
Right. So now we transition to what I call the ground game. So we got to get ready to recover this capsule. That requires working with the US military because we're coming down into an Air Force range. So we're dealing with all the logistics of how we get out onto the site and how we're going to collect the capsule and bring it safely to Houston, to NASA's Johnson Space Center. The team there is busy building state-of-the-art curation facilities and some new analytical laboratories. And we're beginning the process with the science team, which is international in scope, involving many nations across the world, on how we're going to divvy up the sample, which laboratories are going to perform which measurements, and how do we really start to address some of our fundamental questions about this asteroid and more generally asteroids across the solar system.
There are 65,000 known meteorites in collections in museums and universities around the world. And of those, we think around 99% come from asteroids. And they can tell us so much about the diversity of the asteroid belt, from meteorites made mostly of iron that tell us that some asteroids are just cores of planetesimals, to meteorites that are made of a much more porous and volatile rich material, the carbonaceous chondrites, that tell us that some asteroids are really water rich and organic rich. So meteorites are an incredible resource for learning about the asteroid belt. And there was a super exciting thing happened on the 28th of February 2021 this year. This massive fireball was observed over a lot of England and Wales coming in. So it was reported by over 1,000 eyewitnesses. It was also seen on CCTVs and door cams, all sorts of things. And as well as that, it was also recorded by meteor camera networks that are cameras pointing at the sky, looking for exactly this sort of event. And from all of this data, we could reconstruct, firstly, where the fireball was heading, so we could work out where a meteorite was going to land. And also, we could reconstruct where it had come from. So quite unusually for fireballs, because we don't usually have enough data to be able to do this. We managed to work out this fireball actually came from an orbit in the outermost part of the asteroid belt out towards Jupiter. So again, this gives a really good link between a meteorite and asteroids. And having that information about where it came from makes it really so much more scientifically valuable. The meteorite fell as a shower of material over an area a few miles wide. The biggest bit landed into the driveway of a family that live in the middle of Winchcombe Town in the Cotswolds. And it actually fragmented when it landed, and it just became this pile of dust and rubble. So as well as collecting all of the little bits of meteorite, we also brushed up the tiny bits of dust that were on the driveway using a toothbrush to get every tiny little teensy bit up. And also, because it left a little crater, we're hoping to be able to remove the whole part of the driveway so that we can keep this piece of driveway with a little crater in it as one of our museum exhibits as well. So that was the main bit of the meteorite. And then several universities from across the UK went on a field trip to look for extra bits of the meteorite. And a team from the University of Glasgow found a sizable piece, over 100 grams, in a sheep's field. And as soon as my colleagues and I saw it, we were jumping up and down excited because we could see straight away it was so dark, it was black, and we knew this was a carbonaceous chondrite. And these are my favorite meteorites because we think these represent our best examples of what the early solar system looked like. So they've stayed cold their whole lifetimes. And so they're just a frozen relic of what the beginning of the solar system looked like. They've been in a geologically dead asteroid for 4.5 billion years. And they're made up of constituents of early solar system materials, what was floating around in the protoplanetary disk before the planets were around. So we're super, super excited to have this meteorite to analyze. And we've developed an analysis team to look at it in more detail. And one of the things that was quite striking and timely was looking at it. It's really black and it's got little white speckles. It looks very reminiscent of material brought back from asteroid Ryugu by the Japanese space mission Hayabusa 2. So Hayabusa 2 returned back to Earth in December 2020, bringing back about 5 grams of pieces of the C-type asteroid Ryugu. And just the simple visual similarity of them is quite remarkable. So we need to do more analyses of both the meteorite and Ryugu material to look at their similarities and differences. But the timing is fantastic because we can use our meteorite to do rehearsal analyses. And the final thing to say is that we have the meteorite on display at the Natural History Museum, which is free to enter. So anyone in London can come and have a look at it and see it in the room called the Vault at the Natural History Museum.
Asteroid Vesta is the second largest body in the asteroid belt. Only asteroid Ceres is larger. Because Vesta is so big, it can sometimes be seen from Earth with the unaided eye, despite being very far away, orbiting the Sun between Mars and Jupiter. Vesta was the first asteroid to have its mass measured. In 1966, a much smaller asteroid called Arete passed fairly close to it. Vesta's gravity shifted Arete's orbit slightly, allowing astronomers to calculate the larger asteroid's mass. As it turned out, Vesta is very massive. It makes up an estimated 9% of the mass of the entire asteroid belt. In July 2011, the NASA mission Dawn settled into orbit around Vesta to begin a year-long series of investigations. Dawn learned that the asteroid contains a large metal core beneath the rocky exterior, making Vesta a kind of mini-planet.
Hello everyone and welcome to Asteroid Day Live 2021 and our panel on what's inside an asteroid. I'm Lucy Green, and I'm joined by an expert panel of guests, and we're going to take you on a journey inside asteroids. And we're going to discover that there's a lot more going on in there than you might think. Now, dedicated asteroid missions and various ground-based observing campaigns have brought us a long way from thinking of asteroids as this uniform population of solid rocks in space to now knowing that they come in a wide variety of shapes, sizes, composition, and internal structures. And in some cases, curiously, asteroids behave more like a fluid than a solid object, which just seems to make them incredibly alien places. To bring us completely up to date with the science, I have a distinguished panel of guests with me today. I have Julie Castillo-Roges, who is a planetary geophysicist at NASA's Jet Propulsion Laboratory. I'm joined by Naomi Murdoch, a planetary scientist at ISAE Supero. We have Patrick Michel, who is Director of Research at CNSRS Côte d'Azur Observatory. And we have Christopher Sneed, who is an advanced small particle processor at NASA's Johnson Space Center. So Patrick, if I can start with you, not all asteroids are solid, are they? Really curious. Tell us about that.
Yeah, in fact, we thanks to the space mission that occurred recently, like Hayabusa 2 and OSIRIS-REx, we found that effectively these objects are incredibly rich in terms of geological features on their surface. But so far, we never had any direct measurement of an internal structure. However, we could measure the bulk density of some of them and compare them with meteorite analogs that we have on Earth. And what we usually find is that their density is much lower than the one of the meteorites, which means that they may have some voids, some porosities to reduce their density. So that's why what we think now is that the big objects were born big. Initially in the inner solar system, when the planets started to accrete, some objects started to accrete and reach very quickly 50 kilometers to 100 kilometers in size. And that formed the first asteroids. However, the smaller ones come from the disruption of these large asteroids. And we were able to simulate that. And by simulating disruptions of large asteroids, what we found is that in the impact energy regime that occurs in the asteroid belt between Mars and Jupiter, typically we first shatter the object into very small fragments, which are of sizes at most 100 meters in size. But then when these fragments are ejected, their relative velocity is enough low that they can reaccumulate together due to their own gravity and form agglomerates that we call rubble piles. So now our current understanding is that effectively these objects and the reason for their low density is because they are actually rubble piles that are formed by reaccumulation of fragments coming from the disruption of large asteroids.
So these rubble piles then have a much more complicated history than we might initially appreciate. I mean, I'm certainly used to thinking about asteroids as being kind of the debris left over from the formation of the solar system. Is it actually more complicated than that?
Yeah, it's more complicated because in fact, they experience collisions all the time. And therefore there is a sort of collisional cascade. We start from big bodies, then these bodies are disrupted, generate smaller bodies, which themselves are again disrupted, etc., etc. However, one thing which is very interesting is that when we look at the heat experienced by the object when they are impacted, it's not enough to change drastically their composition. So that's why even though the structure of the asteroids is not pristine, their composition still reflects the original composition of the solar system because they never experience much heating for the small ones. So that's why, thanks to sample return missions to these bodies, by getting back samples back, we can really go back to the initial stage of the solar system, which is recorded in their composition.
And Patrick, you're also the lead scientist on ESA's HERA mission, which is going to look directly inside asteroid Didymos in 2024. Tell us how you're going to do that.
Yeah, this is absolutely exciting because this is the first time that we will really measure directly an internal structure. So far, as I said, we think these bodies are rubble piles. They have the voids inside, but we don't really know how all this is distributed, what we mean by voids, etc. And this is very important in order to really understand how they form. And with HERA, we will launch a a spacecraft with 2 CubeSats, and one of them carries a low-frequency radar. So we'll be basically probe into the asteroid using a radar and doing tomography like we do to investigate the interior of our bodies. So this is really, really exciting because this has never been done and will answer a lot of questions we still have.
Brilliant. I'm really looking forward to seeing that mission launched and getting the first data back. And the HERA mission will also deploy a number of small CubeSats to land on Didymos. And I want to move us on to our next speaker now, because she knows that landing on an asteroid is completely different to landing on a planet because the gravity is much lower. So Naomi, I want to bring you in, and you work on a number of missions, including NASA's InSight Mars lander. So tell us a bit about landing on an asteroid and how different it is to landing on a planet. And is it true that it can almost feel more like a splashdown than a touchdown?
Well, yes, the almost absence of gravity when we go to the surface of these low bodies really changes how materials behave. And it's something that makes it really difficult to use existing theories in order to predict the outcome of events like landing or touching an asteroid. And one example of that is a few months ago, we had the OSIRIS-REx mission that took a sample from the surface of asteroid Bennu. And during the sampling event, the spacecraft solely came down to the surface, touched the surface, and much to the surprise of everyone, the spacecraft felt almost no resistance at all from the surface. So it just kept on going. And in fact, the surface of Bennu seemed to have behaved like a fluid, sort of flowing out of the way of the sampling device rather than resisting it. And so, yeah, I guess you could say in the case of Bennu anyway, the surface definitely seemed to have behaved less like rocks and more like water.
And you're involved in a number of experiments to recreate this behavior on Earth. Tell me about those and what you found.
So in our team at ESA Superior, we use both computer simulations and experiments to study the behavior of asteroids and specifically the behavior of the surfaces of asteroids. And for example, we use a variable gravity experiment. So it's basically a drop tower rigged up with a system of pulleys and counterweights. So we can change the effective gravity in our experiment. And we use that to try to predict and recreate spacecraft asteroid interactions. And so what we know is that most asteroid surfaces are covered with granular materials, things like sand, dust, gravel, and we call it regolith on the surface. And our recent results have indicated that granular materials behave very differently when we reduced gravity. And the reason is that you go to low gravity, you take away the weight of the particles, so you reduce this downwards force that the particles have. And this in turn reduces the friction between the particles. So that means that with really little interparticle resistance, the surface can become fluidized much more easily. And the consequence is that when we go down to touch it, we can actually penetrate into the surface much more easily, and we can penetrate much more further as well into the surface in low gravity compared to in terrestrial gravity. And it's exactly what the OSIRIS-REx mission experienced.
And these experiments, is it the case that they're part of the NEO-MAPP program? If so, what's that program about?
That's right. So the NEO-MAPP program is a large international project funded by the European Union's Horizon 2020 Research Innovation Program. And as part of NEO-MAPP, we are increasing the maturity of several spaceborne instruments specifically designed for asteroid exploration. We are working on advancing our understanding of the response of asteroids to external forces like impacts. And we're also developing some brand new tools and techniques that will be used to analyze and interpret the data from future asteroid space missions, such as the HERA mission.
Brilliant. And talking about the HERA mission, the CubeSat part of that mission, what is it that the CubeSats are going to tell us?
Well, one of the really exciting things about the HERA CubeSats, in addition to the radar that Patrick was mentioning earlier to look inside the asteroid, is the fact that they're going to go down and touch the surface of the asteroid. So we can use, remote observations like images in order to make educated guesses about the asteroid physical properties. But by directly interacting with the surface, that allows us to truly probe those mechanical properties. And this is something that's really important for planetary defense strategies and also for asteroid science, trying to understand the evolution of these bodies. And so one of these CubeSats, one of the HERA CubeSats called Juventus, actually has an accelerometer that's specifically been chosen to measure the landing impacts, or the impacts if we happen to bounce. And so with this accelerometer, we're going to measure how hard we land on the surface, how far we penetrate in, how long it takes us to stop moving. And from this, we can actually determine a wealth of information about the asteroid surface.
Brilliant. Thank you so much, Naomi, for that. Let's move on now to bring in our next speaker. And one asteroid that has received a lot of attention over the years, and that's Ceres, the largest known asteroid with a diameter of just under 1,000 kilometers. And in fact, it's so large, it's actually also classified as a dwarf planet. And NASA's Dawn mission studied Ceres from 2015 to 2018 and found that it was a remarkable world in its own right with some fascinating internal properties. So Julie, I want to bring you in here. Tell us why Ceres is so special and what you believe is inside it.
Yeah, thanks for asking. Yes, Ceres is definitely very different from the near-Earth objects that we just discussed. It's clearly more like an icy moon, and there is a very big chance that actually it came from the outer solar system. We found chemicals at the surface of Ceres that are telling us that Ceres probably did not form in its current place. And then we found that Ceres has about 50% of its volume is water in some form. And it might have 40 kilometers of an icy shell, which is similar to an ice shell we can find at icy moon in the giant planets.
I was going to say, because you're talking about the interior there and the high level of ice within this this asteroid, but I believe it was some strange surface features that first gave you the clues to this interesting interior. Could you tell us about those surface features? What were they?
So I think you're referring to the bright deposit that we found in a few places, and especially in a big crater that is called Locator crater. We found with the Hubble Space Telescope, so almost 10 years before Dawn got to Ceres, we found these white spots, and so we were very curious about them. And then they started to resolve into many more white spots when Dawn got close to Ceres. And they are made of salts, and especially sodium carbonate. We found also sodium chloride, so more like table salt at the surface of Ceres. And what is fascinating is that this material is really concentrated in just a few places. And we think that they were brought in from the deep interior through fractures created by the impacts that created in Locator crater.
So these bright spots on the surface are really telltale signs of the fact that water exists on this asteroid or in this asteroid.
Yeah, that's right. So we think there are what we call brines, so very salty water right before Locator crater, probably at 40 kilometer depth. So, but then there is a way by which this liquid is getting to the surface, and it's something we're trying to understand using the Dawn data, but we're also working on a new class of missions that would allow to get a better understanding of what's going on there.
So you mentioned there that, well, of course, that the Dawn mission is over now. And so thinking about future missions, you're the principal investigator for science of another NASA mission, NEAR-Scout. Could you tell us about this mission and what you hope to achieve with it?
So Dawn explored Ceres, which is the biggest asteroid in the main belt. And NEAR-Scout is going to probably investigate the smallest asteroid that has ever been explored by a space mission. Our target is between 5 and 15 meters. Based on astronomical data. So it's way smaller than, for example, Bennu or even Itokawa. And so, yeah, we're very excited about that. The big deal with that mission is that it uses a new propulsion system, which is a solar sail. It's 10 by 10 square meter solar sail. So it's a little bit challenging because everything is new with that system. It's the first deep space CubeSat. Beyond the moon, we had to invent everything almost from scratch, and we just finished the integration and testing of NEAR-Scout like 1 month ago, and we are in the verification phase. And before we ship the spacecraft to the Kennedy Space Center, and we hope that it's going to launch at the end of the year.
Brilliant. Not long for us to wait then. Another super exciting mission. But going to asteroids is one thing, but actually recently we've been starting to actually bring back samples of asteroid material. So I want to move on to our next panelist now. So Japan's Hayabusa 2 mission returned samples from the asteroid Ryugu in December last year, and NASA's OSIRIS-REx, that we've heard about, is currently heading back to Earth with samples of asteroid Bennu. So what do we do with those samples once they're back here on Earth? And this is where I want to bring in our next panelist, Christopher. Christopher, tell us about your job in the curation department at NASA's Johnson Space Center.
Sure. So most of the materials that we collect from space are curated in facilities all over the world, but many of them are at Johnson Space Center. The most notable collection is the Apollo samples that were returned between 1969 and 1972. And we've been curating those for about 50 years now, over 50 years now. We also have other collections of Antarctic meteorites, cosmic dust that's been collected in the stratosphere. And more recently, we've collected solar wind samples from the Genesis spacecraft and comet dust from the Stardust spacecraft from Build 2. And we're now preparing for these two new collections, these asteroid collections from Ryugu and from Bennu.
And I mean, that's a broad range of samples that you're storing there and curating. Is there a big difference between the way you would store, for example, the Apollo moon rocks to how you would store asteroid samples?
Yeah, so there are a few significant differences, but the main thing that we want to do is we want to keep these samples free from oxygen. We don't want oxidation of components. The big difference between the Apollo samples and the asteroid samples we're returning is we also don't want the organic components in these asteroid samples to be changed by microbial activity. So if you have little bacteria or bugs that eat and process the organic compounds over time, that will change your chemistry. And that's something that we didn't worry too much about for Apollo, but we're really worried about for these organic carbon-rich asteroid samples.
And given that you've got, this fantastic collection, what are some of the things that you hope to learn from being able to study asteroid samples, in situ in the laboratory?
So the main thing that we want to learn is really what these components look like and what they tell us about the formation of the solar system. So an analogy I always give is that if you had never seen a cake in your life and you encounter one for the first time, you'd be curious about how it was made. You might be able to eat it. You might be able to taste the sweetness in it, but you really wouldn't have a lot of evidence of how it was made. But if you went into a room and there was a cake and there were also some eggshells, sort of an almost empty measuring cup with milk in it, some sugar, you'd begin to understand what went into making this cake. So asteroids and these asteroid samples are the leftovers of planet formation. And they let us know in a way that we couldn't study just from the planet itself, what went into making these things.
And when you're studying your samples, do you need a lot of material or is just sort of a few grains or a small collection of grains enough for you to do your analysis?
So this is the great thing about how sample return has changed as a result of analytical technology. When the Apollo samples came back, you'd have tons of material and people would, for some analyses, dissolve entire rocks in acid and get data from that. Now with micro and analytical techniques, we can use really micron and even submicron sized particles to tell us something significant about the cosmochemistry. We find grains that survived incorporation in the solar system and still record their pre-solar signatures. So you really don't need a lot of material now. So for instance, the Japanese mission, the Hayabusa 2 mission, brought back about 5 grams of material. And that could presumably last for the next half century of analysis. And for OSIRIS-REx, hopefully we got something like 0.5 kilogram of material, and that should last at least as long as the Apollo collections, because these micro analytical techniques give us a lot more mileage on these samples.
Well, that's fantastic. It just goes to show that we need the technology to advance hand in hand with, in order to be able to advance our knowledge. So thank you so much to all panelists in this very brief discussion, but it's been extremely illuminating and extraordinary to find out just how exotic these mini worlds really are. So thank you, a huge thank you for all your time. You've really brought these fascinating places to life for us. So that's the end of this panel, but Asteroid Day Live has a lot more in store for you today, including how we are going to be deflecting asteroids in the future and how asteroids could spark a new economy in space. So stay tuned and happy Asteroid Day.
There are many paths to becoming an asteroid scientist. I mean, you could be a chemist like me, a biologist or a natural science person, and want to understand the molecular makeup of these asteroids to try to understand what's actually on them. What were the formations 4.5 billion years ago, the chemical signatures that were actually there that helped start life on our planet and maybe even other planets. Geology is another path, you know, being a geologist and understanding these rock formations and how they were actually formed, how they broke off of other planetary systems and were put in these orbits, or an astrophysicist, a mathematician, you know, understanding the trajectories and the orbits of these hurtling and tumbling rocks full of metals and gases and things. And so there are many paths, but I think the most critical path is just to be a lifelong learner and curious as to what's up there and how we can solve problems, explore, and make our life better in this universe.
The Chamber of Commerce Group is here to protect your interests as well as those of the Luxembourg economy. We represent 90,000 businesses in Luxembourg, 75% of salaried employment and 80% of the GDP. We weigh in on all new legislation that can impact you. We bring together all stakeholders involved in the creation and development of your business, and we are committed to providing qualified personnel through vocational training and continuing education. We can help you go international thanks to our partnerships with specialized professionals. We are one of the leading publishers of economic information in the country via a wide variety of advanced communication tools. We are a force for change, federator, facilitator. Come pay us a visit. We are here for you.